Related rates, section 4.1. Example of the radius of a circular oil slick, r equals 7 feet, is increasing at a rate of dr dt of 4 feet per second. Assume pi is approximately 3. How fast is the area increasing? Okay, so the area of a circle, pi r squared, and if we take the derivative with respect to time, we're going to get dA dt is equal to pi times 2 times r times dr dt. Okay, so pi is approximately 3, so this is going to be 3 times 2 times r is 7 at the point that it's 7 feet, raised to 7 feet, r is 7, and it's times 4. So it's 2 times 3 is 6, 4 times 7 is 28, 28 times 6, 8 is 48, carry the 4, 2 times 6 is 12, 4 is 16, so it's approximately 168 square feet per second. Okay. Okay, so this is an example of related rates. You have a formula, take the derivative with respect to time, and you have two rates here. We have derivative of area with respect to time, and the derivative of the radius with respect to time. Okay, so do another example. Airplane traveling at dx dt, 600 feet per second, is passing 800 feet directly over an observer. How fast is the distance y between the plane and the observer changing at the moment the plane passes overhead? Okay, so so we can use Pythagorean theorem here. The y squared is equal to 800 squared plus x squared, and at the if we take the derivative with respect to time, we have 2 times y times dy dt equal 2 times x times dx dt. And at the moment that the plane is passing overhead, y is the distance between the observer and the plane. The plane is directly overhead. Y is going to be 800. So, and x is going to be 0. So we have 2 times 800 times dy dt equal 2 times 0. And dx dt is 600 feet per second times 600. So if you solve, so that it's 600 dy dt is equal to 0. Divide both sides by 1600, and you get dy dt is equal to 0 feet per second. Okay. Okay, so part B, let's redo this, but let's find the how fast y is changing after 1 second. So after 1 second, now the plane has traveled 600 feet and is no longer directly over the observer. So let's pull out another piece of paper here. Okay, so we can use the same formula we had before. We have 2y times dy dt is equal to 2x times dx dt. And now, after 1 second, after 1 second, we have 800 we have the plane has gone 600 feet. And so that means that y has to be the square root of the distance between the observer and the plane has to be square root of x squared plus 800 squared. So y is root plus 800 squared dx dt dy dt. Okay, so if x is 600, then y is going to be 2 times square root 600 squared plus 800 squared dy dt. 2 times x is 600 and dx dt is 600. Okay. So we can cancel the 2's here, and this is just going to be 1,000. So we have square root of 600 squared plus 800 squared. 6 squared, and I'll just do out the arithmetic. We have 3,600 plus 6,400. 64, no, need a couple more zeros here. So it's 6 times 6 is 36, and then we double the number of zeros. 6 times 6 is 36, double the number of zeros again. Okay, so this is going to be 36 plus 64 is 100, so this is going to be square root of 100, and then 4 more zeros. So it'd be 1,000,000 times dy dt equals 36 followed by 4 zeros. Okay, so then if we take the square root, we take half the number of zeros. So the square root of 1 is 1. 246 would be 1,000. 1,000 dy dt equals 160,000. And divide both sides by 1,000, and chop off 3 zeros. So dy dt is going to be 360 feet per second. So so 1 second after the plane passes overhead, now the plane is over here. The distance between the plane and the observer is changing at a rate of 360 feet per second. Okay, so that's the second example of related rates. I'll go over another example. So this is same situation, except for, we're going to now focus on the angle. We want to know, so the plane is passing at 600 feet per second, passing directly over an observer, 800 feet in the high, same as before. But instead of the distance, how fast the distance is changing, we want to know how fast the angle is changing. So the angle here, theta, the angle between y and the vertical line. So so we could do the tangent theta is going to be side opposite over the adjacent, so the tangent theta is equal to x over 800. And then take the derivative with respect to time. Derivative of tangent is secant squared. So secant squared theta d theta dt is equal to derivative x is just x. So as just 1 rather. So this could be 1 over 800 dx dt. Okay, so okay, so we want to solve for d theta dt. So if we multiply both sides by cosine squared, that'll give us the cosine squared will cancel here. We get d theta dt is equal to 1 over 800 times cosine squared theta dx dt. The cosine of theta is the adjacent side over the hypotenuse. So y here is going to be the hypotenuse here is the square root of x squared plus 800 squared. Okay, so okay, so the theta dt 1 over 800, and the cosine squared is 800 over the hypotenuse. So the adjacent height over the hypotenuse, so it's going to be 800 squared over x squared plus 800 squared dx dt. Dx dt is, well, dx dt is 600. So times 600. Okay, so at the moment the plane passes overhead, x is going to be 0. So if you evaluate this when x equals 0, we have d theta dt is 1 over 800 times 800 squared over 0 squared plus 800 squared times 600. This is just 1. 800 squared divided by 800 squared is 1. So we just have 600 over 800, which reduces to 3/4 radians per second. Okay. Okay, so that's how fast the angle is changing at the moment the plane passes overhead. 1 second after the plane passes overhead, then so we can use the same formula for d theta dt. D theta dt 1 over 800 times 800 squared over x squared plus 800 squared times 600. But after 1 second, now the plane has traveled 600 feet. It's traveling 600 feet per second, so now x is at 600. So this is going to be 1 over 800 times 800 squared over 600 squared plus 800 squared times 600. We computed this before already. This is would be 1,000 squared. So it's we can put the 600 with the 800. So it's 600 over 800 times 800 squared over 1,000 squared. So there could be some cancellations. The 800, this 800 will cancel with one of the 800s on top, and we have let's say 670 is 48. actually, let's do it this way. We'll reduce this fraction here. This is 3/4, and this is 8 over 10 reduces to 4/5. So it's 3/4 times 4/5 squared. And this is one of the 4's will cancel on the bottom and the top. So we'll have 3 times 4 over 5 squared. And that's going to be 12 over 25. Writing this wrong. Equal to 12 over 25 radians per second. Okay. Okay, so another example of related rates. A 60-foot wide by 100-foot wide, 100-foot long swimming pool is being filled at a rate of 1 cubic foot per minute. The depth varies from 4 feet to 12 feet. A cross section of the pool is shown below. Maybe this is where the diving board is, where it's 12 feet deep, and then the lap lane maybe 4 feet deep. We want to know how fast the water level is changing when the deepest part of the water is 4 feet deep. So at 4 feet, we're going to be in the triangular portion of the pool. So the bottom 8, just based on the diagram, the bottom 8 feet are going to form a triangle. So this is this is 8 here, and the it's 100 feet on top. Okay, but we're only filling it up to so far. It's only filled up to 4 feet. So this is 4 feet here. But these so we have a triangle within a triangle, and they have the same angle. Actually, the same angles. So the sides are going to be proportional. So so this is up to 4 feet. So, but let's call this x. It'll be x is up to 4 feet. So x over let's call this the base. X over the base is going to be equal 8 over 100. They have to be in the same proportions. So so if we solve for x is equal to 8 over 100 times the base. Actually, so x is equal to, if we reduce that, it's 2 over 25 times the base. Or if we express, maybe it's more convenient to express base in terms of x. Base is equal to 25 over 2 times x. So the area of a triangle is is 1/2 the base times the height. So in this case, it's going to be 1/2, and the base is 25 over 2 times x, and the height is x. Okay, so we get 25 over 4x squared. And then if we take the derivative with respect to time, we'll get another sheet of paper here. Yeah, so we have the area of the triangle, the cross section. 25 over 4x squared, and we want the volume of the cross section. Well, this pool is 60 feet wide, so the volume is going to be 25 over 4x squared times the width of the pool. So it's going to be, the width of the pool is 60 feet. So it's 25 over 4 squared times 60. 4 into 60 goes 15, so 25 times 15 times x squared, 25 times 15, 125, 225, 375, 375 x squared. That's the volume. So then if we take the derivative with respect to time, that means dv dt is going to be at 375 times 2 times x times dx dt. And then we know dv dt. We want to solve this for dx dt. So this is this is 750 times x times dx dt. So then if we solve for x, that means dx dt is 1 over 750 x times dv dt. Okay, so so at when x is 4, so dx dt then would be 1 over 750 times 4, and dv dt is 1. The water being filled at pool is being filled at a rate of 1 cubic foot per minute. So dv dt is 1. So this is 1 over 3,000 feet per minute. Okay. 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 For part B, same situation, but now we want to know how fast is the water level changing when the depth is 6 feet. Well, it's the same formula. It's dv dt, or dx dt rather, is going to be 1 over 750 x dv dt, and now we put in a 6 here, so it's 1 over 750 times 6, and dv dt is just 1, so 750 times 6, 0 divided 30, 4,500 is 1 over 4,500 feet per minute. Okay. So at 8 feet deep, we're kind of on the boundary between the triangle portion and the rectangular portion of the pool. So the top 4 feet are form a rectangle. So this is going to be on the boundary between the two. So we have a triangle portion here, the first 8 feet, and then we have a rectangular portion on top of that. So so we'll try it using both ways. We'll use the compute the rate using the triangular portion, and then the rate using the rectangular portion. So anyway, so for the triangular portion, portion at the boundary. Again, we use the same formula before. Dx dt is equal to 1 over 750 x dv dt. So that's 1 over 750 times 8, and dv dt is 1. 750 times 8 is 6,000. 1 over 6,000 feet per minute. Okay, so that's as x approaches the boundary from the triangular side, the rate is 1 over 6,000 feet per minute. But we can also compute the volume on the rectangular portion. So on the rectangular portion, we have the volume is equal to length times width times the height, and the height is going to be the same as the depth of the but it's going to be minus 8. So it's going to be length and width are fixed. So we have the length is going to be 100 feet times width is 60 feet, and the height of this part of the portion of the triangle is going to be we could write that as let's say x minus 8. Okay, if we consider that the x to be the depth from the bottom of the pool, then that the depth on just this portion of the pool is going to be x minus 8, and at the deepest point. So this is going to be 6 times 1 is 6, and you have 3 zeros, 6,000 times x minus 8, or it's 1,000 x minus 48,000. Okay, so then if we take the derivative with respect to time, we get dv dt is equal to 6,000 dx dt. And if you solve for dx dt, you get dx dt equals 1 over 6,000 dv dt. So at the triangular portion, the pool is changing at a constant rate. This dv dt is 1, so this is 1 over 6,000 times 1. So it's 1 over 6,000 feet per minute. Okay, so on the triangular portion, the height, the rate of change of the height changes. So at 4 feet deep, it's 1 over 3,000 feet per minute. Then at 6 feet deep, it's 1 over 4,500 feet per minute. And then at 8 feet, it gets up to the theta is 1 over 6,000 feet per minute, and then it stays at that. On the rectangular portion, it remains at 1 over 6,000 feet per minute. So part D at 10 feet, it's still the same formula, right? So it doesn't. It's going to be constant over that particular between depth 8 and 12. It's constant, so it's dV dt, or dx dt rather, is equal to 1 over 6,000 feet per minute for x between 8 and 12 feet. It's constant over that interval. Okay, so another example 5. Sun sets at a rate of 1/4 radians per hour. How fast is the shadow of a 60-foot tree increasing when the length of the shadow is 4 feet? So we have a picture here. Here's a tree 60 feet tall. X is the length of the shadow. Theta angle is the angle of the sun. It's the setting sun. And we can get the hypotenuse of this triangle by square root of 60 squared plus x squared. Okay, so we can use write down a formula involving theta and x, and we can use the there's a couple of trig functions we could use here. One of them would be the tangent. Tangent theta is equal to 60 over x. So we need some kind of formula relating theta and x. So a tangent function is convenient enough here. So that's we can write that as 60 times x to the negative 1 power, and then we want to take the derivative. So it's derivative tangent secant squared, and then we're times d theta dt. So we want the derivative with respect to time, and this is equal to we can use the power rule here. Minus 1 comes out in front. Minus 60 x to minus 2 times dx dt. So we can write this as secant squared theta d theta dt is equal to minus 60 over x squared dx dt. And what we want to know is dx dt. So if we solve this for dx dt, we get dx dt is equal to minus x squared over 60 secant squared theta. Let's secant squared theta d theta dt. Okay, so let's express secant squared theta in terms of x. Secant is the hypotenuse over the adjacent. So this is going to be we'll have this is minus x squared over 60, and the hypotenuse is be 3600 plus x squared over x squared d theta dt. Okay, so the x squareds will cancel. So we can write this as minus 1 over 60, 3600 plus x squared, and d theta dt was given to be 1/4, and it'll be negative because the sun is setting, so the angle is decreasing. And negative 1/4 times negative 1 over 60 that'd be 1 over 240, 3600 plus x squared. So now we can plug in the length of the current length of the shadow. It's 4 feet. So x is 4 feet. So this is it goes 1 over 240, 360, 3600 plus 4 squared. And get another piece of paper here. Okay, so this is it's going to be equal to 3600 plus 16 over 240, 3616 over 240, 240 into 3616, 1 times 240 is 240, remainder 121 brings down to 6, going about 5 times, about 1200, remainder 16. So it's about 15, a little over 15 feet per second. It's approximately 15 feet per second. Okay, so if you want to also do this when the length of the shadow is 30 feet, so we could use the same formula. So dx dt is equal to 1 over 240, 3600 plus 30 squared. 30 squared is 900, so it's 1 over 240 times 4500, 240 into 4500, 1, 240, 0, 1, 2, maybe close to 9, let's see, 9, and then 4 is 36, give it 3, 9 times 2 is 18, well, it's close to 9, it's 9 is a little too big, right? So it would be about approximately 19 feet per second. Okay, the length of the shadow is 100 feet, dx dt over 240 plus 3600 plus 100 squared. 100 squared is 10,000, so this would be 1 over 40. 1 over 40 times 13,600. And if we divide 240 into 13,600, let's see, maybe it goes 6 times. No, not quite, maybe 5 times. 5 times 0 is 0, 5 times 4 is 20, carry the 2. 5 times 2 is 10, 2 is 12. 0, 0, 6, 1, remainder 160, bring down to 0. So maybe 6 times, 6 times 0 is 0, 6 times 4 is 24, 12, 14, 60, 160. So yeah, close to 57. We get repeating 6s, so say approximately 57 feet per second. And that concludes this presentation.